Hi, Professor. This is Ethish. This is my ID. Sorry, as you can see, my ID number is 999901804. So my project is about iris flower dataset classification using machine learning algorithms. So coming to the project, just a second. So the iris flower dataset, or it's also called as the Fisher's iris dataset, because Reynold Fisher has introduced this dataset in the year 1936, and there have been a lot of researchers have gone through on this dataset and still going on this dataset, and it's a well-known dataset. So coming to the iris flower, on the iris flower we have like three categories. So iris versicolor, iris setosa, and iris virginica. So in these categories, in these three categories, the setosa stands apart from these two, versicolor and virginica, as we can see in the further slides. So the setosa, and we can differentiate the setosa and versicolor virginica easily, but differentiating the versicolor and the virginica is a bit difficult because their values are pretty close to each other. And these are the parameters that I've taken: sepal length, sepal width, petal length, and petal width. So the sepal length is nothing but the uh, edge of the flower, and the petal is the entire flower. Okay, so in this we have taken some descriptive statistical measurements like the min, max, median, and the square roots and all, and then the class distribution. So we have taken enough amount of data to train our models, and enough data to test the model so that we can get to a particular result, an appreciable result. And we have taken a lot of attributes in them. So just taking the petal length and these parameters, we have got these box graph. So in this box graph, this the first box graph is for the sepal length. So we can see with this box graph, so the range lies between from starting from 1 to 8, and the most of the range of the most of the size the petals have is around 5 to 7. In between that, the sepal length is around that. And coming to the sepal width, we have some outliers in the sepal width. We see a lot of dots outside the range, so these can occur some errors. With this can occur some errors, and because of these errors, it's really difficult to differentiate the versicolor and the virginica because of these outliers, and the petal length and the petal width down there. So this is the histogram on the same parameters. So most of uh, uh, the values are pretty same, and you can easily differentiate which one is what. So the scatter graph between the sepal length and sepal width will come to this. I'll come to this at last. So let me show you the program. So I've imported all the parameters, all the libraries that I want for these, for the initial understanding. So I've taken this iris data set in here, iris data set, as you can see, and this is the shape. It has 150 rows and 6 columns in them. So the and this is the present. This is the table. So this is the description of the data set that I've taken. And initially, whenever we start uh, uh, putting or training a model, we usually check for null values so that those null values don't cause any errors in the further. As you can see, there are no null values in there. The dataset is fine, and then I have taken just the top 5 values so that we can see what details that we have in there. So I'm this is the first 50, and in that first 50 I'm taking 100 as a trial. So I'll train and test these 100 values. um, just looking for the number of, so we got each 50 values of Setosas, 50 values of Virginica and 50 of versicolor, and just plotting a graph. So uh, usually they share 33.33% because they are all 50-50%. And now the box plot that I was talking about in the presentation, this is that. See, we have got some outliers. This causes error in differentiating the Virginica and versicolor. And this is a axis plot I have done. So with this plot, we can easily understand that most of the range lies in between here, and very less amount goes, like very less amount of the petal size is here. And these are just the box plots, and this is the violin plot, which gives us a better understanding of the values. So the setosa flower, the petal length is more on the setosa compared to versicolor and virginica. And when you compare it with the sepal length is more in the virginica and versicolor when it's compared to setosa. So that's a major difference. So we can easily differentiate the setosa and the setosa with the virginica and the versicolor species. But differentiating these two is a bit difficult. And coming to these plots, these just give you a basic understanding. The blue one is the setosa, the orange one is the virginica, and the green one is the versicolor. So you can pretty much easily differentiate them uh, with whatever parameters that we take. And this is the heat graph. Basically, it gives you a better understanding of where the most of the values stand. And in here I have reshaped the sepal length and the sepal width to train them. So this is the graph that we got. So all the values that are lying in here are setosa, the sepal width of the setosas, and the values that are lying here are the sepal widths and the values of the virginica and versicolor. And these are the algorithms that I've taken: linear model, linear regression, k-nearest neighbor classification, and I've taken SVM in SVM in here, and some distance classifiers, all the different classifiers that I've taken here, so that we can have a better understanding like which of the algorithm is performing better with these data set. So here I've created the training data set. This is a training data set, and that training data set I've given to the logistic regression, and the accuracy that I'm getting on logistic regression is 0.97. That's a great accuracy, I would say. And using these as a confusion matrix, not so good on this, but that's fine. And the SVM that I'm talking about, the support vector, this is this algorithm, I like it more because with the support vector you can differentiate the values in a three-dimensional space, and the accuracy that I'm getting on with the support vector machine is pretty good one. It's 0.97. Because it's a data set that's well known for years, we can get a good amount of accuracy on that as well. And with the k nearest neighbor, that's the same thing. And the Gaussian naive Bayes, this is where uh, the accuracy got completely 100%. And I like using Gaussian Bayes, and most people suggest using Gaussian naive Bayes. We also call it the general naive Bayes, which is good for the iris data set. Most people suggest that because we have a continuity in the values in the data set. So Gaussian naive Bayes is better for data sets which have continuity in them. And Using decision tree also does a pretty good job with this kind of continuity data sets, and the data set which are not in discrete. And you can say like Gaussian naive Bayes is also good when we have dependent values, let's say like true or false, yes, no, and these kind of like the binary situations where we have the Gaussian naive Bayes or the general naive Bayes. It's pretty good over there. The Gaussian naive Bayes and the SVM, the support vector machines. The Gaussian naive Bayes and the support vector machines, these are good for this data set as far as I've got my results. Here's a comparison of the all the algorithms that I've taken in here. So you can see the logistic regression, naive Bayes and everything. So they are pretty much close to each other, and they pretty much do the good work on the data set. But when it compares to the efficiency and time complexity, and the faster, which algorithm is faster compared to the other, I would say the naive Bayes and the support vector machines are better for these kind of data sets, or where there is continuity and which are not discrete. This is my conclusion on this project. And coming to here, so this is what we have talked. So these are the libraries that I've used, and these are the algorithms that I've used. Yeah, and this is the final output that I've got. And finally, I would say thank you for giving me this opportunity, and I hope my project, you like my project, and um, I hope you, if I'm missing something or if I'm lagging on some, uh, if I'm lagging on some, let's say like some more algorithms that I have used, or should I be using the different data sets for these algorithms so that I get a pretty good understanding on how these algorithms work and how I can put algorithms in these classifications and go into deeper roots of these algorithms, um, like pushing them to their core, I would say. And finally, thank you for giving me this opportunity, and I'll close my session now.